Hello everyone. In the previous lesson, we delved into the disassembly and assembly of small three-phase asynchronous motors, gaining a certain understanding of the overall structure, principles, working conditions, and states of three-phase asynchronous motors. These motors find common applications in our daily lives and various industrial processes, often playing a pivotal role in automated control systems. Now, let's explore how we drive and control these motors. Using the fundamental control circuits for three-phase asynchronous motors. In the upcoming sessions, we will be focusing on the basic control circuits for three-phase AC induction motors. Through this learning journey, we will be able to practically apply motor control concepts and master essential electrical engineering skills. Let's start by acquainting ourselves with electrical control systems. Electrical control system circuits are commonly referred to as secondary control circuits for electrical equipment. They encompass different control circuit configurations based on specific equipment. To represent the design intent of electrical control systems for industrial machinery, we use graphical depictions that illustrate the electrical components and their wirings. This representation is known as an electrical control system diagram. Electrical control system diagrams incorporate both textual symbols and graphical icons. These symbols, serving as a unified language in the field of electrical engineering, are internationally standardized to establish a common vocabulary. The primary types of electrical control system diagrams are electrical schematic diagrams, electrical component layouts, and electrical installation wiring diagrams. Electrical schematic diagram, a diagram that illustrates the interconnections and electrical operational principles of various circuit components. Electrical schematic diagrams consist of the main circuit and auxiliary circuit. The main circuit constitutes the high current pathway in electrical control circuits. On the other hand, the auxiliary circuit encompasses the circuits beyond the main circuit in control systems, typically involving lower current levels. Electrical component layouts, these show the actual installation positions of electrical components as indicated in the schematic diagrams. They provide essential information for installation and maintenance purposes. Electrical installation wiring diagrams, these represent the practical implementation of electrical schematic diagrams, utilizing standardized graphical symbols to illustrate the layout and actual wiring of electrical components. The basic control circuits for three-phase AC induction motors are built upon the concepts of electrical systems. Moving forward, we'll delve into some commonly used low-voltage electrical devices that you will encounter in these circuits. Electrical devices are designed to modify circuit parameters manually or automatically in response to external signals and requirements, enabling control over the circuit. Low-voltage electrical devices, specifically, operate within circuits rated at 1200 volts or DC voltage of 1500 volts and below. They serve functions such as switching, protection, control, and regulation within electrical systems. Low-voltage electrical equipment has a wide range of applications, with different structures and operating principles. First, let's get acquainted with contactors. Contactors, classified into AC and DC types, are used to frequently establish or break the connection of main AC or DC circuits over long distances. Their primary control targets are electric motors. In the circuits we will be exploring, we'll focus on AC contactors. An AC contactor consists of an electromagnetic mechanism, a contact system, an arc extinguishing system, and external structures. The electromagnetic mechanism comprises coils, springs, and an iron core, converting electromagnetic energy into mechanical energy to accomplish circuit disconnection. The contact system includes main contacts and auxiliary contacts, working in conjunction with the electromagnetic mechanism to disconnect the circuit. The arc extinguishing system's role is to eliminate the arcs generated during circuit disconnection, preventing internal short circuits. When the coil in an AC contactor is energized, the electromagnetic mechanism generates energy to attract the moving iron core, thereby changing the state of the contact system's contacts. When the coil is de-energized, the contacts in the contact system return to their initial state. In electrical diagrams, the symbol for an AC contactor is usually denoted as Km. The graphical representation of the contactor's coil and contacts is shown as you can see. A low-voltage circuit breaker, belonging to the category of switching device, commonly referred to as an air switch, is used for power distribution, infrequent motor startup, and circuit protection. These breakers consist of an operating mechanism, contacts, an arc extinguishing system, and various releases. The operating mechanism is responsible for external circuit control. Different releases enable various internal circuit protection. This is a release device along with a detailed explanation as you can see. The electrical symbol for a low-voltage circuit breaker is represented by the code QS, and in electrical system diagrams, it is typically depicted using its normally open contact as shown in the following diagram. Similar to household fuses, fuses are designed based on the principles of the Joule effect and the thermal fuse operation principle of heating elements. Widely used in low-voltage circuit systems, fuses are connected in series in protective circuits. When a short circuit or overload fault occurs, the current flowing through the heat fusing element generates heat, leading to the melting of the element and the subsequent disconnection of the fault circuit, thus providing protection. In electrical diagrams, the symbol for a fuse is generally depicted as Fu, representing the overall appearance of the fuse. Thermal relays, a subtype of relays, function by utilizing the Joule effect. They disconnect the motor circuit in the case of excessive overload, providing protection for the motor. The principle involves incorporating a normally closed contact with a heating element into the circuit. In prolonged overload situations, the heating element opens the normally closed contacts, thus implementing overload protection. However, thermal relays have thermal inertia and cannot respond to short circuit faults in the circuit. In electrical diagrams, the symbol for a thermal relay is often designated as Fr. The symbol represents the heating element within the main circuit and the normally closed contact in the auxiliary circuit as you can see. Control buttons serve as prime examples of master control devices. They are used to manually emit signals, momentarily connecting or disconnecting small control currents to contactors, relays, and other devices. Control buttons typically feature both normally open and normally closed contacts, comprising elements such as press buttons, reset springs, and contact systems. To indicate the functions of buttons and prevent misoperation, different colors are often used. Red is used for stop or emergency stop buttons. Green indicates start buttons, black represents jogging control buttons, and blue is generally reserved for reset buttons. If the reset button has a stop function, red color should be used. In electrical diagrams, the symbol for a control button is often depicted as SB. Commonly used control button graphical symbols are illustrated as you can see. In this lesson, we've gained an understanding of electrical control system diagrams, along with knowledge about low-voltage electrical devices commonly found in the basic circuits of three-phase asynchronous motors. In the next lesson, we will delve into the jogging circuit for three-phase asynchronous motors as an example to study electrical control system circuits. That concludes this lesson. Thank you, everyone.